So this is the BME680 gas sensor, and it is an extremely tiny component measuring just 3 by 3 millimeters with a height of just 1 millimeter. So it will consume hardly any space on your printed circuit board, extremely small with the metallized can. And the metallized can actually has a hole at the top over here, which you can see. This hole actually allows for the air to diffuse into the sensor, where it is then able to measure the pressure, the temperature, the humidity, as well as the gas composition. If we flip this chip, what we see on the back side is a land grid array pattern of 8 pins. These pins are primarily the ground pin, the power pin, and the I2C interface pins. So what we'll do now is we will move to get this can removed and then start looking inside in a bit more detail at the design of how the sensor has been put together. So without much ado, let's delve into it. So once you've taken off the metal lid, the internals of the BME680 gas sensor are visible. What we see over here is an interesting scenario where we have a true system in package design. We can clearly see that inside the device we have 3 silicon chips, basically 3 devices which are positioned together. So you have 2 dies on the left hand side which are placed on top of each other, so that's a stacking arrangement, and you have this 1 die on your right hand side which is sitting next to these 2 dies. So in total we have 3 dies in this device. The way this is structured is that you have, if I can just position this properly, your bottom device, which is this one, is roughly around 1100 microns by 1700 microns, so 1.1 millimeter by 1.7 millimeter chip. And this is your amplification application specific integrated circuit, which provides you with the necessary filtering, the control over these different sensors, and the communication with the outside world via the electronic interfaces. What you have over here after that is your top die, which is your 3-in-1 sensor chip. So this is this die which we're looking at over here is your pressure sensor combined with humidity sensor combined with temperature sensor, and this device is roughly 1.1 millimeters by 1.3 millimeters in dimensions. The middle bit, which is the large area occupying over here, is your pressure sensor, and you have your membrane inside over here. Then you have the 2 humidity sensors on this, as well as your 2 temperature sensors on the side, which are your diode based sensors. What is also interesting is that in order to cater for the system to be in such a small package, you have your MEMS micro hot plate, which is your MEMS gas sensor, is sitting on the side over here. This is a roughly 600 micron by 900 micron device with a micro hot plate in the center, which is then coated with a metal oxide, so that when you have these oxidation and reduction reactions taking place over here, you can detect the gases. And essentially you have 2 probes going for heater design, and you have 2 for picking up the change in resistance, and we'll talk about this in a bit more detail when we zoom into these devices. So essentially at this point, what I'd like to say is that we have 3 devices in a single package, which is then laid out, connected through bond wires, and you get a 3 by 3 millimeter device at the end. So let's move on into each of these devices individually and see what they look like. So I've zoomed into the micro hot plate structure, and as you can see, we have a chip which is roughly 600 by 900 microns in dimensions. Along with that, what is really interesting to note is that you have this center area, which is your membrane area. So if you just measure these dimensions over here, we can see that this is roughly 325 by 325 micron membrane. which is a square membrane. It's a closed membrane, so that gives you more mechanical robustness as compared to a suspended membrane. But what is interesting also to note is that the droplet, the metal oxide solution which has been dropped on top of it, right in the center, is actually very nicely positioned. So you're not getting much overflow of this droplet. And if you can measure the dimensions of this, we can see that it is an 85 micron radius droplet, which is nicely positioned right in the center of this micro hot plate. We have two wires connecting for the heater, and we have two wires, these two essentially are for the heaters, and then you have the readout from the interdigitated electrodes which are sitting on top of the micro hot plate's heated region, and then they pick up the change in the resistance of the oxide layer as it interacts with the analyte. The membrane is extremely thin, and the temperature range is roughly in the range of going up to from 200 to 400 degrees. So 400, I would say, is probably the top range for this kind of a device. If you go over that, you're likely to occur a lot of radiative losses, because radiation is a T to the power 4 and then multiplied by area. So as soon as this small region even begins to heat, it's T to the power 4, and that creates a lot of radiative power loss. So it is an extremely small device, and it is very interesting to see that this is developed using MEMS technology in a very small package, which is sitting right next to two other dies. So let's look at the pressure sensor and the humidity sensor and the temperature sensor die in a bit more detail now. And I'll zoom out and I'll zoom back into the other die now. So back on this pressure sensor die, what we can clearly see over here is a region which is your membrane region, which is extended it's very hard to look at it, but it is visible nonetheless. And this is roughly your membrane region, which is around 620 microns by 620 microns. So you have a Wheatstone bridge configuration where you have the sensitive elements sitting on the edge of the bridge of the membrane essentially, and as it flexes, you're able to pick the change in resistance. What we also notice is that on the side we've got two diodes over here which are picking up, measuring your temperature essentially, and below them, so if I can just delete this, below them are your two humidity sensors, and these are essentially working as in capacitive mode. Most likely they are they've got a thin polymer film deposited on top, and the below them are very fine interdigitated electrodes running across the length of this humidity sensor. If I were to measure the dimensions of this, we can clearly see that this is very tiny. This is 300 microns roughly by 130 microns. So two of them together, most likely being averaged out, but can't say for sure without any further details. And the same is happening on the temperature side as well. So if we zoom out from here, move back into the temperature based devices, we can see we've got two of them over here. Again, if we were to measure their dimensions, we're looking at roughly 60 microns by 235 microns in dimensions. It does have a date code of 2014, so that's interesting to note. But they are still very much available on the market and very much available for sale. So with that in place, unfortunately it would be very difficult to remove the top die and go to the bottom ASIC. So we're going to leave that as is for this video, and in the next video we'll look at how we are going to be we'll study the next sensor from here, which is the BME680 essentially in this change, where you have artificial intelligence integrated into the BME6 into the gas sensor. So don't forget to subscribe, and see you in the next video. Bye bye.